Okay, thank you. I'll hand you over now to András Kabai.
Okay, hello everyone, greetings to you. Today I will talk about fault injections against embedded systems. A couple of words about the topic and why I've chosen this, because it is important. Hacktivity opened a dedicated day for embedded security, which is quite important change and a good progress in case of these hardware security related areas. So this is something that has huge impact on the hardware security and embedded security. So this is one of the key points why I've chosen this. Another one is that I like hardware hacking, so I do this at home. I have my own research lab and research corner at home, and this is something that I also do at work. So with regards to the agenda, there will be basically three main areas covered. We'll get a short intro, but really just a quick summary into the fault injection attacks. Then there will be demonstrations with regards to the voltage glitching against the Trezor and the EMFI related attack against the UDS diagnostic service running on an automotive ECU. So a couple of words about me. Well, it turned out that I don't have too much funny-looking pictures about myself, so I have to choose between a suit and tie company profile picture or this. So considering the event, I chose this, but trust me, I'm a friendly guy despite the picture. I'm a director at the Cyber Services at the Hungarian Deloitte, and I'm responsible for the special services that cover basically car hacking, automotive security related services, and hardware hacking services. So besides traditional penetration testing, we do have a specific and specialized lab equipment and a specialized team who are dealing with this kind of projects, and we are delivering projects worldwide. So, fault injection in a nutshell, what it is, what the hell it is. So electronic components like CPUs, microcontrollers tend to work and expected to work properly in a range of a safe zone. This is coming from a specification. It can be a voltage range, so the typical voltage that is expected, for example, by a microcontroller or a CPU can be moved in a small range, and below that or above that, something unexpected or non-deterministic could happen. Or this could be something else as well. This could be also temperature. So CPUs, microcontrollers, other components are qualified to work properly in a range of a safe zone. This is the main message. And outside of this safe zone, there is something magic that could happen. And fault injection attacks are typically trying to bypass these borders and move at the sharp edge of the border to find the exact spot and exact configuration, the exact environment and settings that is necessary to let the target keep up and running, but to achieve something unexpected that let us, the attacker, to achieve something meaningful and bypass some security features. So there are various types of fault injections. The typical ones are the voltage glitching. This will be also covered in the demo. For voltage glitching, we are typically targeting the target's power source. Typically, if possible, we tend to go directly to the core voltage, because that is a different one that is used by, for example, the external interfaces. And we introduce glitches, some shorts, for example, to the ground on the power lane. There is an electromagnetic fault injection, EMFI, that releases big and powerful electromagnetic pulse close to the chip surface and generates some current inside of the chip die and could flip, for example, some bits in registers or in memory, which could falsify the information that is transferred on the bus. Or there are, for example, other attacks in fault injection like the clock glitching, when, for example, we introduce also again a glitch, additional unexpected clock signal in the external clock of the target that is out of the space range and enforces, for example, the CPU to try to execute the next commands while, for example, data between the registers are not yet moved. So this is something that can be exploited. And these were all non-destructive attacks against the targets. But for example, there is one, the optical fault injection, where you have to perform typically chip decapsulation to have a direct view to the chip die and use a focused laser to the right point on the chip die to the silicon and introduce glitches and faults to the chip with optical laser. How it looks like? Oh, coming back to the main graph here. So this is a very generic representation of the fault injection. There is something, the timeline that exists in case of every attack, and there is a trigger point that belongs to the given attack. It could be an authentication probe, it could be a power on reset, it could be anything that you can use precisely or as a starting point to fix your attack in time. And using this trigger, you start to count typically precisely, so there is no jitter enabled here to perform a successful attack, and you start to count, and after a specified amount of delay, you execute the attack. And the attack depends on the fault injection type. In case of voltage glitching, the green line here is the VCC, the power of the microcontroller or the CPU. In case of VCC, and the voltage glitching, you somehow insert a glitch here. This could be injected in several ways. Typically, a very fast switching MOSFET is used, for example, to short the VCC line to ground, and basically, for a very small amount of time, it reduces the available power that is available and can be used for the CPU core. And because of this, it could malfunction. If it is too long, the attack is too long, then there are built-in electronics and detection that can detect and react to the unexpected voltage changes and could, for example, reset the target itself. So you have to be fast enough to be sure that your attack is not detected, but long enough to have the right impact on the target. In case of EMFI, the attack is basically the same. The only difference is that you don't target the voltage of the target microcontroller or CPU, but you introduce electromagnetic pulses. But basically, you have to follow the same approach. Wait for a trigger, count until the specific delay, then execute the attack with the right configuration, and we will get back to this later, against the target. So, fault injection in a nutshell, continued. What a successful attack could result in. It's very interesting because no one expects this, but a successful attack against a microcontroller or CPU could easily result in skipping an instruction, changing in data that is being processed by the core. So for example, data that is transferred from memory to registers, or the next instruction that is being fetched before executed. So these are all faults that could happen and that could turn the code and command execution to a direction that is valuable for an attacker. So what can we do really with this? So if you check, for example, some loops that you introduce in code sections, we will see it later, where you specify a point that what you would like to exclude from the command execution, then you can turn the whole firmware or code execution to a totally different way. And maybe because of this, you can bypass a security check, you can re-enable, for example, a log debug interface, you can basically do a lot of malicious stuff against the target. There are typical tools that are often used to execute these attacks. The most well-known are the new AEs products, the Chip Whisperer, Chip Shouter, Pico EMP tools. Pico EMP is a quite cheap one that can be also built by your own at home. So it is a DIY friendly tool set and affordable for hobbyists as well. The others are a little bit expensive solutions, especially if you go for more commercial and professional tools that are available on the market. But you can also build your own solutions, and I will show you on the demo videos that how quite cheap and affordable products available on the market can be turned to effective glitchers. So let's see how the glitching could work against some sample code bases. So here we see two very trivial code parts. One with regards to a firmware checking and one with regards to authentication checking before doing anything. In case of firmware checking, for example, when the target has a secure boot and only boots a firmware that is digitally signed and verified prior to executing the firmware. There could be, depending on the implementation, a check like this at the very beginning of the firmware. And it checks, for example, the whole content stored in the flash before execution and checks the signature, whether it is proper or not. And if not, then it gets stuck in an endless loop. So problem solved. If there is unexpected custom firmware deployed to the target hardware, then no one expects that non-trusted firmware can be executed, right? Let's see that later. There is another solution here where before executing a privileged functionality, we check whether the given session or user or whatever else is authenticated or not. And only access to that given functionality is possible if the right conditions are present. But what if we introduce fault injection and target these codes by FI in the given sections? So by introducing, for example, a fault injection attack at that point, as we learned in the previous slides, we can skip an instruction. What happens if in the endless loop I skip, as a result of a fault injection attack, an instruction that jumps back to the beginning of the loop? Then we will break out from the endless loop and continue the firmware execution there. Or what happens here? If the authenticated subroutine is false, then basically sensitive functionality is not stored. But if we are able to manipulate somehow the result of this evaluation and get back a different result because of fault injection attack, then we can get to this functionality and call a privileged function without actually being authenticated. So this is why fault injection is very powerful, because software-based security can be bypassed by hardware-based attacks. I've prepared two demos for you, as I noted. One will be executed against the Trezor 1 hardware crypto wallet, and another one will be executed against the automotive UDS diagnostic service that is running on a custom ECU. So the first one is to unlock the microcontroller using the Trezor one to basically regain debug access and control over the microcontroller unit with SWD access. The second one is to bypass an authentication that is checked before executing a privileged functionality to, in such case, let us open a door in a car. Important to note that these are not novel attacks and no novel hacks here. These are just selected for demonstration purposes, and there are some relevant work in this area that were already done and presented prior to this presentation. But basically, in this setup, there is a totally different tool set and implementation and other approach to target this. So let's go into the details. I think all of you know this target. This is a Trezor 1, well-known crypto wallet, open source, open hardware, very nice stuff. By the way, they have a very good and responsive team. They react to security issues quite fast, and the development they did with the firmware is very good. So they have a quality firmware. So from software perspective, it is very nice. there you can see also some security features and countermeasures they use. For further information and details, you can also go to their official site and check the details. So it could be a secure device by assuming that everything works properly and appropriately based on the spec and the definitions. So let's see what kind of microcontrollers they have and what kind of security features it provides. The STM32.205 is a generic purpose microcontroller, basically. It has a security feature called RDP, read data protection, read protection, and it has basically 3 different levels. Level 0, where there is no protection, so everything is allowed. You can connect to the boot ROM, you can to the bootloader, you can connect to the SWD, to the debug interface, you can refresh the content, you can extract the content, and so on. So there is no protection. There is RDP1, where the access to the debug interface still exists, but it is quite limited. So you still have access to the RAM, for example, but don't have access to the flash. Still, you can refresh the device, but that will, for first, purge and mass erase the content, and then you can write a new firmware to that. Most important info is that firmware and store secrets in flash cannot be extracted. And there is level 2, a complete lock, and the hardened version. When everything is logged and protected, it is not possible to connect to the bootloader, it is not possible to connect to the debug interface, and the flash is, of course, protected. So, besides protected, it is irreversible. I don't know how much it is readable, but as soon as you turn your microcontroller to RDP2, it is irreversible as per the data sheet. Another important thing is that the status of the RDP is coming from option bytes. In case of option byte AA, this is RDP level 0, no protection. CC, that's level 2, complete lock. And anything else but AA or CC, it is level 1. So what can we do with this? The attack would be to downgrade somehow our target to RDP1, because a single bit change from CC, any single bit change from CC will let us downgrade to RDP1, or if we are super lucky, then to RDP0, but most probably to RDP1. So let's see what can we do with this. This is how a booting of the microcontroller looks like. And there is a bunch of information here. I'm going to explain the details. So the option bytes in modern microcontrollers and configurations tend to be stored not in fuses that are just configured one time, but in flash. So they are referring sometimes to them as fuses, but actually they are not fuses. They are stored in flash. That will be important later. The boot process looks like this in case of a microcontroller. Whenever it receives a power, it starts to prepare the internal peripherals and the whole architecture for be ready for execute commands. As soon as every internal setup and configuration is ready, the reset line, the negated reset line from low goes to high. And this is the point from where the core of the target, the CPU, starts to execute commands. So the yellow line is the reset line that you see here. The blue or grayish line is the voltage of the core of the target. So as you can see, as we hit this point when the microcontroller started, it starts to process something. And the pattern changes here and here. Basically, there is a boot ROM burned into the microcontroller, so it starts to execute the boot ROM for first, and after that, it reaches a point here, it will start to access the flash and load
content from the flash. And because accessing flash and reading out information in the flash is consuming more power, this is why you see different voltages and the, bigger fluctuation on the voltage line. It is important to note that to get this kind of information, you have to remove some components from the board because decoupling capacitors usually flatten out. Decoupling capacitors have the target to be stable, even if there is a small variance in the voltages. But that is, for us, for analyzing and for attack, is bad because capacitors are working against us. So we have to remove these decoupling capacitors at the right point. And now we can see something like this, and we can perform attack effectively. So here we know that most probably flash access is happening. Probably it reads the configuration and option bytes here, and after that, if everything is up and running and configured according to the stored settings, the application code, the exact firmware is started to be executed. So we have, from the actual start of execution of the boot ROM to the flash access, about 200 microseconds to wait. So this is probably the time we have to wait until we execute the attack. Then we have this amount of time, which you can see the horizontal scale is about 50 microseconds, and this is about one slot, so it is about a 50 microsecond slot to execute the attack, the glitch itself. And let's see what we can do with this and how to achieve that. Going after the details in the datasheet, you can see how the power supply looks like, power supply scheme looks like, and the target. And basically, it can be figured out that there is a point, VCAP1 and VCAP2, where we can basically have direct access to the internal core's voltage. So if we have access to these capacitors that are installed to that pins and remove those, then we can perform glitching directly on the core voltage. That is very important because other voltages provided from external pins other than these pins will be sent through the internal voltage regulator that will basically filter out kind of our attacks and glitches, and we need to directly have impact with the better results and better quality glitching directly on the kernel, the CPU. So going after the datasheet, the schematic, and the PCB, because it is open source hardware, it is quite easy to locate the right capacitors at the schematic, figure them on the PCB, and also identify all of those additional points that will be interesting in the attack. So we need SVD access for the debug, and we need core voltage to target basically the device. So this is what you can see here, the interesting points and capacitors that need to be removed. Additional ones, for example, installed to the reset line needs to be also removed because it has direct impact on the curve on the reset. And as we are planning to trigger our attack to the reset, this capacitor also works against us. So after removing these components, picture for the scale, so you have to work with this kind of small SMD capacitors or even smaller ones. The target is ready for being evaluated. And just a pro tip, because I run into troubles previously sometimes, always use a target device that survived your preparation and don't spend hours on debugging on why the target chip did not react to the attack. So let's see how the test setup looked like, and I hope you understand now why I did not provide you a real-life attack here. This is not that kind of setup that is easy to move or transfer, very sensitive to every move and short, small changes. So we have basically a Raspberry Pi that controls the whole attack. It has a Jupyter notebook running in, from where with a custom Python script I can control everything. There is a Trezor one, of course, which is the target. FPGA, this is the iStick development board, where I have a custom Verilog and a bitstream downloaded to the FPGA that is acting as a precise timer from the trigger to execute the actual glitching. There is a DUD interface that I'm running as a GDB server. This is connected to the Trezor 1. It runs, by the way, at this setup Blackmagic Probe open source firmware. And this is used to access the debug interface once it is unlocked. There is a glitcher electronics which contains analog multiplexers to fast switching between different input voltages and N-channel MOSFETs to let us short the voltage to ground. And of course, we have some oscilloscope probes connected to the right and interesting points to trigger to watch how the setup works and how the process is going on. So quick recap on the setup and how it is being executed, the attack. The Raspberry Pi controls everything. It is connected to the remote GDB service on the DUD board. The FPGA is configured by the Jupyter notebook as well. And the Raspberry Pi is also responsible on the power cycle of the target. So whenever it is needed after executing every attack, it turns off and on the power to the target. And the FPGA, as soon as the MCU is recovering after power on, triggered by the reset line, starts to count. And after hitting the right delay, it will control the glitcher electronics and insert a right glitch with changing pulse length and changing delay to the target. So this is how it looks like. And let's see. The demo. So the demo. Yep. So this is a test setup. Does it run? Oh, come on. Okay. The test setup that contains basically the Jupyter notebook, the external camera for the target. And what I do is basically walking through on the custom code I implemented here, just executing them. This is just some kind of function supporting the target. Here I open basically a GDB session for the remote service, and they're basically just checking whether SVD is available at the moment or not. And hopefully it will confirm us soon that yes, so the debug access is not available. So we are going forward. These are really just supporting stuff for the FPGA and configuration. And this is the settings that I use in the big loops that iterates over the various glitching settings with regards to the delay, the repeats, the pulse width changes, and so on. So after executing the effective attack at this point, you can see that the scope started to change and update the waves and the Trezor started to reboot. So after every glitch attempt, the target is rebooted, and the glitch setting is iterated to the next one, and the attack is continued until we finally reach the attack. So the center line is about 200 microseconds from the trigger. This is zoomed in the core voltage. unfortunately, because of the light, this is not that visible, but there is a big drop down here close to ground in the course voltage. This is the glitch that we introduced, and we are triggering on the reset line. And basically, we are continuously increasing the delay from the specified amount of time, the width of the pulse length, and so on. And we are iterating over and over and over on the configuration. And here I am speeding up a bit the video, because there are two time-consuming parts of the fault injection attacks. One is the preparation, and another one is the execution. Wait until it gets succeeded. So, and this is a very well fine-tuned, prepared environment, so I made a lot of experiments to find the sweet spots. So usually you leave your environment and the equipment there even for days or weeks to find the right configuration. So, getting closer to the end of the video, hopefully somewhere here, we will find the sweet spot where our target finally found SWD access on the target. So it is now the command execution stopped because we attached our debugger to the target. So using the GDB session, I'm now executing dump binary memory command, and basically dumps out the memory of the content. And what you can see, it is loaded back from the dumped file. This is nothing else but the USB class memory structure that you can also find, for example, in the Trezor's code. So what it means, we successfully downgraded RDP2 to RDP1, got access to the target microcontroller, which provided us partial access to parts like the SRAM. In such case, because of the firmware version running on the Trezor was not vulnerable, no sensitive information was accessible in this Trezor. However, prior versions of the firmware are suffering from different vulnerabilities that makes access and extraction of sensitive data like the PIN or the passphrase possible with this kind of access. So unpatched hardware, unpatched Trezors are still vulnerable. So with the updated and patched versions, you might expect that you are safe, but there is another way to move forward, because introducing an additional glitch and, for example, attacking the bootloader itself and the bootloader's read memory command, you can basically bypass the security checks applied on the read memory command that checks whether you are in RDP 0 or RDP 1 and extract the flash content. And from that moment, if you are not using passphrase on the Trezor, then basically it is quite easy to brute force the PIN and access the sensitive information there. Important to note that it was just a good candidate, the Trezor, to demonstrate the attack and the effectiveness of such an attack, but it does not directly belong to the Trezor. It belongs to the microcontroller, and every product that is using these kind of microcontrollers or other microcontrollers that are suffering from the same attacks. So let's move forward and talk about EMFI, electromagnetic fault injections. And I'm trying to speed up to make sure that we can fit into the time. So we are targeting an ECU that is a small component in a car. In such case, to do not harm any vendor, we are using our own ECU that we developed for our car hacking training environment. But basically it runs similar features, similar functionalities. It has a diagnostic, XCP, anything else that are often used in automotive. And we are trying to attack this because in diagnostic there are protected and sensitive routines and functions that can be called only after a successful authentication via security access. And we are trying to bypass the authentication on this. So quick security access one-on-one, just to understand what you will see on the packets. Basically, it is a challenge response-based authentication. The seed that is used for that is 27. So basically, this is how it looks like. The client sends 27 plus a security level identifier, like 2701. For that, the server responds with positive response, which is always hex 40 plus to the requested SID. So 27 plus hex 40 meaning 67. So 67, then repeating the same value and something that is in such case the seed. So this is a seed that we received from the remote service. And the client then calculates the right key for the given seed and sends out the security access send key message with the right key to the target. And if the authentication was successful, then the target responds with 2702. Otherwise, depending on the situation, an error code starting with 7F will be received from the target. So this is very nice. This is automotive protocol. You are almost a car hacker now. So how to hack this? What if we introduce a glitch here, somewhere here, because there should be, after sending a key, some kind of validation check against the authentication probe. And if there is something like this and we try to hack this with fault injection, then if we successfully bypass that check, then maybe we can use an authenticated session later to execute something interesting. So with regards to EMFI, it needs a bit of experiment and mapping of the target before a valuable attack can be performed. So usually you have an EMFI tool with a tip at the end. This is the side view, this is the top view. And you have to find the sweet spot, the sweet point on the microcontroller surface where with the right settings that belongs to the voltage you use to generate the electromagnetic pulse, the pulse length, the repeating pattern, the length and distance from the physical representation of the microcontroller unit and the surface is all counting and all needs to be considered and checked. So there is a lot of experiment that needs to be done. Usually the best effort is to run a customized firmware on the same chip in a test setup with an automated tool like XYZ table on a small CNC. And as soon as you find the right spot, then you can use the right settings on your final target by moving to the same location. So this is the nice small setup. How it looked like. There is a small CNC, what I noted to you, the ECU there, the Raspberry Pi that I already noted previously. We have a DUTCAN interface that is basically performing mass authentication probes against the target, so it performs the security access, seed request, and then key send messages. We have the FPGA for the same purpose like previously. We have this is the hardware trigger switch. As we are dealing with EMFI, so electromagnetic pulse, there is a big risk that something could malfunction or be damaged in the close proximity of the device. So there is just additional separation from the custom FPGA and between the chip shouter EMFI tool. So even the trigger is separated with additional electronics. We have the target ECU, as I noted, that is coming from our car hacking environment. There is a servo connected to it, so it represents now the door lock. The chip shouter from new AE and the USB CAN interface that is connected to the Raspberry Pi to let us execute commands through the CAN bus connection if we succeeded. So the overview of the setup and the execution flow is the following. Basically, the chip shouter, the FPGA, and everything is controlled by the Raspberry Pi, the same Jupyter setup but with a different code. And Raspberry Pi launches basically the attack by allowing doodcan to start the authentication. After sending out the authentication probe to the CAN bus, the doodcan also releases a hardware trigger to the FPGA. The FPGA starts to count. As soon as it reaches the appropriate amount of delay, it basically releases the chip shouter, which fires electromagnetic pulse. And if everything goes well, then Dude can recognize that the authentication was succeeded even if it used the same fake key every time. And as soon as this happens, it informs the Raspberry Pi, which at the end of the day let us know, and we can execute the privileged attack. This is as easy. So let's see how it works in practice. So basically the same setup, excluding that we have a terminal here where I'm dumping and filtering for, for the CAN messages, and you can see that I'm switching to external diagnostic interface and try to open the door with routing control, but as you can see, there is a 7F, which is a good indicator for error code. Because of lack of authentication, it wasn't possible. And by executing basically the attack, you can see how the electromagnetic pulses are injected to the target. We are continuously monitoring here what is happening on the CAN bus. And as you can see the patterns, basically 2701s are sent out, then we receive different seeds. Then 2702 with a fake key 1234 is sent out for authentication probes. And basically we always receive 7F error codes that authentication was failed until if you zoom out, you will see that compared to the trigger, there's a lot of time it passes before we execute the actual attack. And finding the sweet spot is just happening here. Where basically the appropriate settings and the magnetic pulse targeted and released against the microcontroller let us be authenticated. As you can see, we get a positive response there. And having this access, we can easily jump back here and execute the same command, which opens the doors for us. So this way, we managed to bypass the authentication on the Unified Diagnostic Service. So as a quick recap, basically, both the EMFI and voltage glitching provided us ways to circumvent security implementations made in software by attacking the hardware itself. There are ways to improve the security, for example, limit the number of attempts of security access and so on, but UDS can be targeted in different ways. So for example, there is the read memory by address where you can glitch the is authenticated checks, for example, to achieve the same results. And the final thoughts about the hardware hacking of these targets and the fault injections, especially the EMFI and voltage glitching, is that these are attacks that are feasible and valuable attacks and should be considered by every vendor. And there is no secure device, no secure product with just only secure software. You could have the best and the most secure firmware ever if your underlying hardware is vulnerable for such an attack, because in such case, fault injections are the one way to circumvent this kind of implementations in security in software. There are some software-related mitigation possibilities to introduce, for example, multiple and redundant checks in condition checks, or store critical information with their complements and always check them against each other when you are evaluating them. This can pinpoint issues when that are introduced by fault injections, and you can react to them appropriately. However, it is important to note that these kind of mitigations always target the application firmware itself, not the hardware software that is the built-in boot ROM, for example. So you can maybe enhance the security of your firmware, and it will be more resilient against these kind of attacks. But if the underlying microcontroller and this boot ROM is still vulnerable to fault injection attacks, then maybe the attacker will focus on that to get full control over the device, even before your firmware is being executed. So that was it. I think I ran out a couple of minutes about my time. So thank you very much for your attention, and there should not be time now for questions, but you can reach out to me at the Deloitte booth if you have any question later on. Thank you very much.
Thank you, András.